Welcome back to our course in stochastic processes. Last time we finished our chapter on martingales, and today we are going to start our chapter about Markov processes. You should know what a Markov chain is, and that will be a main example in this chapter. But we will do it more generally, which means that both time and the state space are general, which means they're continuous. Let's see. So this video is about Markov processes, definition and examples. We have a stochastic process and a filtration. Usually the filtration will be the one generated by X. And we call X a Markov process. Well, in words, Fs is independent of Xt given Xs for S less or equal than T. So only Xs is important. So that's the formula. So conditioning on Fs is the same as conditioning on Xs, which means other information present in Fs other than Xs are not important to determine the distribution of Xt. And what's actually the same is this thing here. So, okay, here I forgot that should here for all measurable A. And it's equivalent to say, well, the expectation of all functions of Xt conditional on Fs equals the same as when I condition on Xs. Because, well, this here is a separating class of functions, so it determines measures. So these two are the same. And for such a Markov process, there are two things we will encounter over and over again, which is the Markov kernel and the transition operator. The Markov kernel mu st from xs to b, that's the probability if you are in xs at time s, what's the probability to be in b by time t. So here, probability of to be in xt in b given xs. So this xs here. Which is then, of course, the same because it's a Markov process as well, exchanging xs by fs. And the transition operator, that's similar. So that's similar than the first two. So the transition operator and the Markov kernel mirror these two equations. So transition operator st f of x. So given xs equals x, what's the expectation of f of xt? And you can also write it down using the Markov kernel. So when you go from x to y between time s and time t, then integrating this over f of y is exactly the expectation of f of xt given xs equals x. Then we need two more things occasionally. So I have two Markov kernels, mu and nu, and mu times nu. That's a Markov kernel from x, well, which is the first coordinate in mu. So that's here. And that's a Markov kernel from mu to e squared. So you have a product here. And that's the probability to go from x to y using the kernel mu times the probability to go from y to z using the kernel nu. And well, you integrate over all y in this a here and from all z in b. So when I use here two Markov kernels from a Markov process, that's the probability when you start from some x to be in some set a by some earlier time and to be in b at some later time. And when you want to integrate out the first coordinate here, you're having here the full state space. And that's then the probability to go from x to a at the later time point. And that's called mu nu here. That's the Markov kernel from e to e. Okay, let's look at some examples. X is a Markov chain here. And that means I have a discrete time. And mu t plus 1. So that's the transition probabilities from time t to time t plus 1. And usually what you do in Markov chains is you have matrices. So this here is a matrix. And E here is also at most countable. So both are at most countable. So pt t plus 1 xy is the probability. If you are at x at time t, what's the probability to be at y at time t plus 1? And of course, when you sum over y, that must be 1. And using this, you can here define the Markov transition, the Markov kernel. So to go from x to some set A, well, you just have to sum over all y in A over the matrices. But also the transition operator here you can write down using the matrix P. So what was the transition operator? That was when I start in x, what's the expectation of f at the next time point? Well, and the probability to go to y is ptt plus 1 xy, that's this thing here, and times f of y exactly computes this expectation of f of xt plus 1. So let me write this also down. That's the expectation of f of xt plus 1 given xt equals x. That's the transition operator. Okay, some more examples. Sums. Well, I have here a simple example. So the x's are independent, and S is the process which arises by summing the x's. That's a Markov process. Yeah, because when, for example, you want to transition, so I'm just writing st plus 1 equals st plus xt plus 1, which already explains. So it depends on the past only via st. That's why that's a Markov process. And how do you compute things? So the probability that you are in A at a later time point, well, given ft, then st has to be in A minus x, and xt plus 1 is in x, then the sum of st and xt plus 1 is in A. So that's the thing here. And you can write down the Markov kernel. So to go from x to A, therefore xt plus 1 has to be in A minus x. So of course, A minus x, that's the set of our y. Y minus x, y in A, like this here. And also the transition operator. So that's the expectation to be in of st plus 1 and st plus 1 when you start in x at time t. So st plus 1 is small x plus capital xt plus 1. And you just need to compute the expectation of this. So that's this example here. Another example, the Poisson point process. That's also a Markov process. To go from x at time s to some set a by time t, well, you have to distinguish all cases. So what can happen? Where you go? You have to go to a, but of course you have to go to x plus 1 and so on. Otherwise the probability is 0. And then you're just summing all possibilities, so all probabilities here. And this here is the Poisson distribution with rate lambda times t minus s. So that's its parameter. So you have it here, you have it here. You are having k minus x jumps because you start in x. So you have to have k minus x jumps in order to be in k. And also here the transition operator. Again, we have this Poisson distributed random variable p. What's the expectation of f at the time point t when you know that you are in x at time s? Well, that's this thing here. The expectation, okay, you start in x, so you will be in x plus p by time t, and that's exactly the transition operator. It's very similar for Brownian motion, actually. The only difference is that increments here are not Poisson distributed, which led here to adding p, but they are normally distributed. And if z here is n01 distributed, this here has an n0 t minus s distribution. And that's the distribution of the increment between time s and time t. Well, and for this reason, the expectation of f of xt, what is xt? Xt is small x if you start in small x, plus such an independent random variable. So that's xt, and you will have to compute the expectation of f of xt, which is exactly this thing here. And in this case, it's even easier also to write down the Markov kernel. So to go from x to a, so how is xt distributed, given I know that xs equals small x? Well, it has a normal distribution with mean x and variance t minus s. And that's exactly what is written here. Yeah. So in all these cases, that's all rather simple. But let us prove something. We are going to prove something when is a Gaussian process or Markov process. And there's a nice criteria, which is this thing here. You have a Gaussian process, which means that all finite dimensional distributions are normal. Then X is a Markov process. If and only if this here holds. So what's that? So I have 3 time points, S, T, and U. On the left-hand side, you compute the covariance between S and U times the variance at time t. And on the right-hand side, you have the covariance between S and T and between T and U. And these must be the same. For the proof, we are using the expectation of at time t, or for all t is 0, and variances should not vanish. And we set something, which is this xu prime, which we will use. And xu prime is xu minus something, and the minus something is made such that xt and xu prime are independent. So first of all, xu prime, because it's a sum over normal distributed random variables, is again normal. And for normal random variables, they are independent if and only if they are uncorrelated. And xu prime and xt, they are uncorrelated because when you compute the covariance between xt and xu, you have the covariance of xt and xu here. So between xt and xu prime, I mean, you have the covariance between xt and xu, and the covariance between xt and xt, which is the variance. So this vanishes here, and you end up having the covariance here, and you subtract the covariance, the same covariance which turns out to be 0. So xu prime and xt are always independent. And now let's see how to prove this. So we start with x is Markov, and then this equation should hold. So first of all, since it's Markov, I have that xu, I'm going to write it like this here, is independent of xu given xt. That's the Markov property. Which also means given xt, since xs and xu are independent given xt, xs is also independent of xu prime given xt. So xs is independent of xu prime given xt also. Now I'm going to show that xs and xu prime, they are completely independent, not only given xt. And the reason is, I can compute the probability that xs is in some a and xu prime is in some b. Well, they are conditionally independent, which means I can write it like this. I can condition on xt, xs is in a given xt, of xu prime in b given xt. But xu prime here is independent of xt, which means for this thing here, so this here is independent of xt, so I can delete the xt bit here. And now that's just a real number. I can pull that out here. The expectation of the conditional expectation equals the expectation, which means that that's the same as the probability of xs in a times the probability that xu prime is in b. So xs and xu prime are independent. So xs and xu prime are independent. Well, but then I have it because that means that the covariance between xs and xu prime is 0. And the covariance between xs and xu prime, well, this is the covariance of xs and xu minus covariance of xt and xu divided by the variance of xt times the covariance between xs and xt. Like this here. Then I can multiply by the variance, which is assumed here to be not 0. And then I have exactly this here. Yeah. So that was one direction. Now the other direction. So I'm starting with this equation and I want to show that x is Markov. So as we just saw, so I'm claiming that this arrow goes also backward. So we saw that if xs is independent of xu prime, the equation here holds. Otherwise, if the equation here holds, I have that this whole thing here is 0, but that's also this covariance. So that means that xx and xu prime are independent. So xs is independent of xu prime. Yes. That also means, so what else? yeah, xs is something which is smaller than, so s is something smaller than t. So xu prime is independent of everything which is smaller than t, which means that xu prime is independent of the full sigma algebra fs as less or equal than t. So that's this thing here. And then I can start proving the Markov property, the probability that u is an A given ft. What's that? Well, xu here equals xu prime plus this thing here. So that means xu prime is something in du, and the other thing, well, this covariance of xt and xu divided by variance of xt, this here must be in a minus x, all this given ft. Here I have to use an x then also, of course. So when I have this, then the sum of these two things here is an a, and the sum of xu prime and this thing here is xu, and that's the probability I want to compute. Well, xu prime is independent of fs as less than or equal than t. So this is independent. And apparently this thing here only depends on xt. That means I can write the same thing here, but condition on xt. Well, now back, that's the probability of xu is an A given xt. And I'm done with this proof here. Let's do an example. Okay, the first example, Brownian motion is a Markov process. Why is that? So remember, for Brownian motion, we had that the covariance of xs and xt equals s minimum t. So since s less than or equal than t less than u, I have here s times t, and here also s times t, which means the two sides of the equation are the same, and the Brownian motion is Gaussian, is a Markov process. There is another nice example of a Gaussian Markov process, which is the so-called Brownian bridge. In the Brownian bridge, you're starting with a Brownian motion, but you don't compute xt, but xt minus t times x1. So when you have t equals 1 here, you have x1 minus x1, which is 0. So yt starts in 0, and at time t equals 1 is again 0. And in between, it behaves like Brownian motion. So here's an example. You start in 0, you end in 0, and in between it just behaves like Brownian motion. Well, the covariance between two time points, well, you can use the definition here. And x is Brownian motion. And let's say s is less than t and less than u. So this covariance is s. That's s. This thing here is s times t. This here is s times t. And this here is again s times t. So s times t is subtracted twice and added once, so you have s minus st, or s times 1 minus t. And using this, I can compute what happens with the equation which we had for Gaussian Markov processes. The covariance of xs and xu, that's then s times 1 minus u. And the variance of yt, I have t times 1 minus t from this equation. But that's the same as the covariance of x, ys, and yt, because this is s times 1 minus t, times the covariance of the x, yt and yu, which is t times 1 minus u. And I am done. So, last topic of this video are spatially homogeneous Markov processes. Here I need some structure on my state space, so E has to be some abelian group. And what is a spatially homogeneous Markov process? That's one, no matter where it just is, it will behave the same in the future as, it will behave the same no matter where it just is. So increments do not depend on the current state. Or the probability to go from x to b is the same as the probability to go from 0 to b minus x. So that's a homogeneous Markov kernel. And a Markov process is called spatially homogeneous if the Markov kernels are homogeneous. Okay. And the Markov process has independent increments. We had it in the Poisson process and in the Brownian motion. If xt minus xs is independent of fs, so that's just independent. And there is a nice connection between homogeneous Markov kernels and spatially homogeneous Markov processes. And that's this one here. If you have a Markov process, it has independent increments if and only if it's spatially homogeneous. Okay, so that's the same. Let's see if we can prove this from right to left. So it is spatially homogeneous, which means the Markov kernels here are spatially homogeneous. So that means that mu st for all possible s and t from x to b is the same as mu st from 0 to b minus x. So that's the case for all x and for all b. And I have to prove that it has independent increments, which means that the probability that xt minus xs is in some b given fs is independent of fs. Well, that's the same as the transition current from between s and t from xs to xs plus b, because then, so that's at time point t, then the difference is just in b, which I compute here. But since my Markov kernels have this property, I can subtract xs from here. That's the same as mu st from 0 to b. Which means that that's not a random variable, that's just a number, which means I can forget about the condition here. Yes, it's an fs measurable random variable, which is a constant, so it's independent of fs. That's one direction. In the other direction, from left to right. So it has independent increments, and now I have to see if it's spatially homogeneous. So first of all, xt minus xs t bigger or equal than s. That's a Markov process. by the Markov property. So it just starts in 0 at time s. It must have the same transition probabilities, and these have the property that mu st from xs to some set b, which is the probability to be in B, given at Fs. So if this here is the case, that's the same as that the increment xt minus xs is in B minus xs, given Fs. And it has the same increments, so that's the same as going from 0. So because here I have this Markov process xt minus xs, it goes from 0 to b minus xs. And this here, right from left to right, is the defining property of a homogeneous Markov kernel. And therefore, it is spatially homogeneous, as defined here. Okay, that was it for today, and next time we will deal with the strong Markov property. See you then.